Okay, so the next speaker is from KAUST, Hong Im. So Hong comes from Princeton University, initially got his PhD there with Ed Law. And then he was a postdoctoral researcher at Sandia working with Jackie Chen. And he did some of the first DNS calculations of multi-flame interactions, something that's becoming more important for variable load operations of gas turbines. And he has since then he has worked at University of Michigan for a very long time. And now he joined KAUST in 2013. And he's a recipient of many awards, including the Career Award and SAE Ralph R. Teeter Award for Educational Achievements. And he's also an Associate Fellow of AAA and a Fellow of ASME. So,
thank you very much. Good morning. So my name is Hong Im. I am part of this organizing team. So I hope you are enjoying all these outstanding workshop. I've been enjoying a lot of these excellent talks given by the pioneers in each subject area. So this talk I'm going to talk about today is coming from the contribution of many of my associates, as well as some of my external collaborators, as you can see here. My talk today will consist of 3 parts. First, I'll talk about some recent computational development I've been making, being ready for extreme simulation. And I'll talk about some premixed flame simulation that we've been recently doing, which kind of is similar to a couple of other previous presentations. And third, I will also put some thoughts on these recent development and regime diagram for auto ignition. So S3D, thank you for Evat for this excellent introduction to S3D. This is co-developed at Sandia, led by Jackie Chen. And this is still one of the best scalable combustion DNS code. So this is just a milestone, how far we've come for the past two decades. So we started off with the 2D simulations, but landmark simulation of 3D lifted flame has been done in recent years, and the Evat simulation could be put on here. And we are getting ready for this next launch of Shaheen 2 and Oak Ridge National Lab. They are preparing for a summit, which is to be commissioned in 2018. One thing you might have noticed is, interestingly, there is about order of magnitude difference in terms of Shaheen 1 and Cray in terms of peak performance, but we were able to simulate about the same size, which means that actually, well, the answer is clear, because we have maybe three major users on Shaheen, but Cray has maybe 300. So we can effectively say that the next Shaheen coming up can have effectively 70 petaflops performance, which is good news for us. So again, S3D is an excellent code, but still to be ready for this next generation massive scale simulation, we need to do some work. So I started this project since I joined KAUST in collaboration with the Oak Ridge National Lab, Ron and Sankaran. The main objective and philosophy is the following. We would like to make the code scalable to even those much larger exascale computing platform. It's got to be performance portable on multiple architectures, because the next generation machines are coming up with all these hybrid GPU, many-core attached to the CPU platform. So we want to be able to utilize them. And the code should be also extensible to multiple applications. So we would like to be able to use, right now I've been mostly working on compressible version of DNS, but we are trying to extend the capability into low Mach number and AMR and so on. In doing that, we recognize there are many useful open source libraries that are at disposal. So we can develop these many important kernels in an accelerated fashion, which can also be reused in multiple platforms of the code base. So this is a kind of some ambitious task, and we've been working on it for about 1 year now. So the basic structure of the code is I named it as a KARFS, a KAUST Adaptive Reacting Flow Solver. Here, adaptive word means a little bit more than AMR. It's adaptive in many different sense. So right now, our immediate plan is a 2-track approach. The straight Cartesian mesh DNS, can think of it as S3D on steroid, except this is completely rewritten in C++ with utilizing a lot of these the high performance architecture. So the black lines are completed and yellow one is in progress, and we are almost near completion of this rewritten version of Cartesian mesh DNS. Also, another track is about the finite volume approach to be more versatile in a real geometry situation, including some AMR and immersed boundary method approaches. And so you can see some of the collaborators associated with each of those subjects. And analysis, another important part. We started working with the Valerio Pascucci and KAUST Extreme Computing Center on those data mining capabilities. So the basic strategies, again, utilize many different parallelism at its best. Well, as you can see, I don't want to spit out too many jargons, but basically there are different layers of parallelism. The standard, the CPU node has MPI, and then there are new kind of many-core. They have thread between GPU thread parallelism. So the idea is we want to expose all those unrealized parallelism to the best. And also even existing CPU-only cases, there might be some less than optimal parallelism. Then we would like to really take the full use of that. So one of the new development is called Kokkos, which is a new paradigm, the new project under this Trilinus project. This is part of the project is led by Sandia Group. This version, basically what it does is it can generate the code that is portable to many different types of memory and execution architecture. And the Kokkos version of so basically, for example, if you can develop this thermochemistry kernel through Kokkos, it can generate the actual source code adaptive to the DNS code in multiple architectures. So we have been doing all this, rewriting all those derivative routines, thermochemistry module, transport modules into this Kokkos framework, and made some preliminary test cases comparison based on the multi-core, which is similar to the new Shaheen architecture, and some latest GPU, NVIDIA GPU platform, which is kind of a main backbone of the Titan, Oak Ridge Titan machines. And also we have explored some Intel Xeon many-core architecture. So speaking of, I'll just give you a couple of examples. I don't want to spend too much time on it, but chemistry kernels, this is one of the things that can be really best utilized by GPU architecture. So what you're seeing here is a huge matrix of isooctane mechanism with 800 species and 3,000 reactions. They constitute this a large, sparse matrix, and which is difficult to manage. A lot of these fast GPU processors, they have shared memory, which is not that big compared to the main memory. So the idea is basically try to reorganize reorganize this matrix structure so that we don't have to access this large-scale main memory from the GPU, which is the main reason for the slowdown. The quick test result of our N-heptane chemistry shows about, depending on how you look, it's always a different apples to apple, not apples to orange comparison when you compare CPU versus GPU. But roughly we can find about 60 to 5 times acceleration compared to the Opteron processors, depending on how many cores you're using in CPU mode. So these are two different versions of the GPUs that we tried. Transport module has been done. We have also tested some relatively simple transport mixture average viscosity kernel based on the, this is a different CPU which is much faster than the other chemistry test cases. And we were able to achieve about factor of 2-3 speed up using the Tesla GPU accelerator. This one thing to note quickly is that it's important to see this is acceleration is still good for a smaller number of the cells, meaning that you don't necessarily kind of, this is similar to a strong scaling test, so we will be able to maintain this scalability and acceleration at any scales. So just to wrap up this first part, I would like to make some point here. So many people, when we talk about large-scale DNS simulation, they're talking about real landmark simulation, who's been doing the biggest ever simulation, which is great. But at the same time, we should also recognize another important role of DNS is doing many cases of the parametric study. So even for the some things that we can easily do today on today's computing power. We can, with the exascale computing, we can do those canonical flame, laminar stagnation point flames. It could be still turbulent. We can run hundreds of those with this exascale. So that's, in my opinion, that's another important role that DNS can play, because every time we get complained about how many cases you got, well, 2, then it really limits our ability to compare against the experiment. So thousands of those canonical simulations can be another new model of this DNS in the future, and that's one thing we should always keep in mind. In doing that, this is where the UQ can come into play big time, because we don't want to do kind of a crapshoot blind search of the 100 different cases. When you run many cases, you want to do it in a smart way. So the UQ algorithm can be an excellent way of guiding us so that we can enhance the knowledge gradient. So that's kind of my message for the first part. So moving on to the premixed flames, again, there have been already a number of presenters before me talking about it. And even this standard channel premixed flame has been done by many people before, including Professor Bai here, who just presented today. We are just trying to do a nice, clean channel turbulent premixed flame. And we are trying to also push a little bit of these boundaries of Karlovitz number that many people already talked about. And therefore, then subsequent analysis of statistical analysis to understand flame speed, behavior, and so on. Another work we are doing at the moment, which I don't have time to present, it's still in a preliminary stage, is the work with Professor Sora Provo-Chaudhuri at the IISc. And we are implementing the Lagrangian flame tracking method. And also, I'll briefly show you the visualization tools that we are recently working on with Professor Valerio Pascucci. So here is basically the 4 cases have been completed on the Borghi diagram. So we try to push the Karlovitz number further up. And so starting from standard laminar flame-like regime all the way to a high Reynolds number, order of 1,000, to a Karlovitz number of hundreds. Well, I must note that there are many differences, different way to define Karlovitz number. So it may sound modest, but compared to previous presentation saying Karlovitz number 3,000, it's a long story, but there are different ways to define it. And I'd like to argue that this has pushed the envelope a little bit further. Not by much, but still, this is probably the closest to the distributed combustion regime. So, which was about 126 based on our definition of Karlovitz number. So here are 4 simulation cases, just to, picture tells 1,000 words. So case 4 is the nearest. I had to, by the way, I had to cheat the grid size so that instead of capturing 10 integral scale LEDs, I'm capturing a couple here. So that's kind of a trick everybody plays. Nevertheless, you can appreciate the level of turbulence increase can create large corrugations. And this one becomes almost like I don't know if I can really confidently call it as a flame. So those are kind of a behavior we're looking at. So we can do a lot of these nice flame thickness statistics, which we are still currently working on. This is work in progress. For example, basically you can roughly say that 1 to 4 is in the in the direction of the stronger turbulence. So the first 3 cases showed relatively the flame thickness based on the progress variable gradient is getting a little bit thinner, interestingly, but the other broadened case actually shows a thickening behavior. One thing I've been investigating for a long time was the standard laminar flame theory. How does the flame speed varies as a function of Karlovitz number? So 1 and 2 cases, relatively mild turbulent cases, show some good correlation, linear correlation, although I was a little bit surprised to find that this curve is going up instead of coming down. But I have seen this before because it's a definition of the displacement speed. And that's why we probably want to use a consumption speed. But you can see that those case 3 and 4 stronger turbulent cases, we find some almost a nebulous, uncorrelated behavior. So this is probably one other the mark to show the flame is getting away from the conventional flamenet regime. Well, so many of you who have done this kind of analysis knows how tedious and time-consuming it can be dealing with this massive data set. So I recently hooked up with Valerio Pascucci, who is spending sabbatical year on campus. And they provide us this interactive data analysis tool, and that you can load up the terabytes of data on your desktop. And especially, they came up with a new data format called IDX. If you write it into this IDX, they provide this kernel to do it. And you don't have to load up the whole data to take a look at it. So that makes the access of the data so much easier. And you can see by just moving the slider, you can sweep through the flame front. This is, again, the level of the resolution can be controlled as well. So that's really can save up a lot of time of our scientific investigation. Just to show you one more example of this, this is showing another, this tool can also do this flame norm integral. So this one shows a histogram of consumption speed statistics. So as you move around the slider, you can actually see on the spot, you can see how these things changes. So we are really looking forward to utilizing this capability for our in-depth analysis of the flame statistics. Okay, so I hope I have enough time. So I was originally not planning on talking about this, but Professor Peter's excellent talk first day motivated me to bringing this up to the subject, because well, as we have already seen from many other talks, auto-ignition characteristics is important, and it is actually becoming more important considering the fact that many of these modern engines pushing for higher efficiency, they are relying a lot more on ignition mode of the combustion, like HCCI, GCI, all of those. So it is really important to understand these ignition characteristics. But my original engagement into this subject was motivated by syngas work that I've been working with Margaret Wooldridge at Michigan. And they're also talking about syngas-based driven gas turbine application. And the shock tube measurements, the RCM measurement ignition delay time was compared against the homogeneous, the Chemkin calculation, and as a function of temperature. They found huge, like 2 orders of magnitude gap as the temperature goes down. So people originally argued, well, this is bad chemistry, blah, blah. There are many, many possible explanations. But actually, the RCM was not the only one who found that out. And there was shock tube study who reported, now the shock tube and RCM, the distinction is getting blurred. The RCM is pushing for the high temperature, and the shock tube is going into the low temperature to cover longer observation time to be relevant to the engine application. So this is one of the examples that was done in Amir Farouk's group, and their shock tube, low pressure shock tube study. They found such a huge discrepancies compared to the computational prediction, especially in this region. Even if we consider those DPDT correction, it was not enough. And the similar finding was reported by the Aachen group as well. So these are kind of all related subject, and in fact, so then the one thing I got engaged into this study was Margaret Wooldridge has been doing this University of Michigan RCM study. What they found using the syngas, they found these 2 different regimes of ignition. One is called the weak ignition with more like a front propagation. And then strong ignition is more like a widespread, nearly homogeneous ignition mode. So they did many, many parametric experiments to find out, then distinguish between different regimes of the ignition. And it turned out the boundaries are clearly mapped out as a function of ignition delay time sensitivity to temperature. And in fact, this actually the idea of how coming up with this kind of criterion was not new entirely. It originally came from an old study back in 1970 by Meyer and Oppenheim. They also found the same thing in shock tube ignition problem. It was called the mild and strong ignition there. Again, same problem. So they were able to identify how the ignition happens. And then the boundary was identified as some constant isolevel value of the d tau dt. d tau is the ignition delay time. So you can run the homogeneous calculation, sweep through the temperature, the slope tells you. I think this sentence taken from the paper really sums it up. What it's saying is that non-uniformity in the mixture is not as important as the mixture overall temperature goes up, because things are everywhere becoming very reactive. So you're not going to expect to, it is less sensitive to temperature variation, and it is too short with respect to characteristic time for transport phenomena. So if flame wants to propagate and make some difference anyway, everywhere else will ignite anyhow. So that is essentially related to the supernova kind of pre-ignition shock phenomena. Everything comes together. So I kind of try to look at it in some theoretical way. So there was my earlier work done by my former student Raman and Sankaran. So I like to kind of shamelessly call it a Zeldovich-Sankaran criteria. Basically, the criteria is simple. Compare the spontaneous flame propagation wave speed, which is defined by temperature gradient, as many of you know, ratio between laminar flame speed. So if this Sankaran number gets larger than 1, it is front propagation mode. If it's less than 1, front doesn't do much, it'll auto-ignite, like in a homogeneous mode. Well, this was based on well-defined deterministic condition. So my thought was, can I extend this criterion to more like a turbulent situation where you have statistical fluctuations? So there goes some scaling analysis. This was a paper that was just accepted to CST a few days ago. So I came up with a scaling argument: eddy size, flame thickness, flame speed, and the Taylor microscale, and the box size. So there are standard homogeneous turbulence scaling relation. And I made some simplifying assumptions here. Again, first assumption is a weak ignition. This ignition is triggered by hotspot, small scale, not by the bulk temperature gradient. And if there is, because a lot of experimental evidence shows that there is no strong preference between boundary region or in the middle of the domain. And also, I wanted to make it simpler that basically the temperature fluctuation is coming from the eddy fluctuation. So velocity, U prime, T prime are just treated the same way. And likewise, the Prandtl number is assumed to be 1, so all the scaling argument between scalar and velocity transport are just treated the same way. So important turbulent parameters, as we all know, one is a turbulent Reynolds number based on integral length scale. And Darmstadt numbers can be defined depending on characteristic chemical time is obvious, it's ignition delay time. Characteristic flow time can be that of the integral eddy or that of the Taylor microscale eddies. And by the way, this DAL is similar to what Williams did in his book, the Williams diagram, except the difference is that his case of characteristic chemical time is a flame time. So there is some factor to be involved. You're going to see that in the final results. I'm just mentioning that right now. So mixing time can be properly determined based on Taylor time, length scale and time scale. So, well, the details are in the paper, so I don't mean to bore you with all this scaling discussion. So fast forward, what I found out was the modified turbulent Sankaran number, which has this Darmstadt number dependence, and K factor, which has exactly the ignition temperature sensitivity right there. Again, TF comes in here because of the translation from ignition to flame time scale. Basically, applying the same Sankaran-Zeldovich criterion, I can say that when Darmstadt number is less than K squared, I'm having a weak ignition, meaning flame front predominant. Other case is strong. However, one other thing is that the one subtle thing, because the mixing properties are more dominated by the Taylor microscale, so Darmstadt number based on lambda also has to come into play, which is also related to DAL by the relation. So we can also talk about the same thing. So there are two different strong ignition scenarios. This is the case where the ignition blob can create a propagation, but still mixing is too fast. So it's not going to go too far. You will have just dissipated away. That's what I call the mixing dominant strong ignition, homogeneous ignition scenario. The one we saw earlier here is a little different. This is a case where Even if you have a flame, the rest of the mixture is also very reactive, they'll still ignite anyway. So what I call it is a reaction-dominant strong ignition regime. So with 3 minutes left, this is final result that I came up with. So again, standard Williams diagram, not Borghi version, but I think I like this one better because it gives us nice non-dimensional turbulence intensity, non-dimensional reaction intensity. When Damkar number is greater than k-square factor, we have reaction dominant strong ignition. When it's too low, you have mixing dominant. There's a kind of a slanted curve based on Taylor microscale argument. It's one third of the slope. So weak ignition, front dominant, pre-ignition phenomena can be happening within this green triangle. Unfortunately, this k-square curve moves up and down. I couldn't figure out what I'm gonna do with that. But this is just a result of making three-dimensional plot into two-dimensional plane. So I have validated this result by mapping out the experimental measurement cases onto the plot. Obviously, there are a lot of assumptions involved because we don't know exactly what U prime, T prime is in the RCM. But they seem to match our predictions fairly well. I have also conducted the 2D simulation in 3 cases. I just wanted to demonstrate what I just said in a visual manner. So weak ignition, you have front propagation all the way. And strong ignition, reaction dominant strong ignition, you will see still some ignition front propagation, but before it reaches too far, the rest of the mixture ignites too. Strong ignition cases, everything just mixes up, nothing happens until real homogeneous ignition happens. So in terms of the relative enhancement of auto ignition behavior, the weak ignition shows the strongest the advancement relative to other nearly homogeneous strong ignition conditions. So that's the kind of basic framework I was proposing, and maybe hopefully this might hopefully guide the setting of experimental conditions for further work. So I have conducted other parametric studies. They all kind of falls into as expected. So this is being kind of finished up in my study. So final remark, just for 1 minute. What I wanted to indicate is unlike the conventional the regime diagram, Damkar-Reynolds, which is kind of static condition, determines the spatial fluctuation level, is not enough to characterize ignition behavior. The ignition sensitivity is another important factor that which introduces extra time scale issues. High K, meaning higher ignition sensitivity mixtures, are more susceptible to weak ignition because the neighboring mixture will be more dormant until significant propagation happens. And which is a case for hydrogen and syngas mixture. So that kind of confirms our original hypothesis that what we observed in the syngas experiment was mainly due to this pre-ignition followed by front propagation. Interesting point connected to Professor Peter's discussion on Tuesday was when your fuel is like N-heptane in the engine condition regime where NTC behavior is prominent, where the sensitivity is nearly 0 or even negative, that's where you would expect to see the stronger ignition. So that can be related to the shock and supernova phenomena. My study didn't include those scenarios because I was mainly trying to explain pre-ignition, the weak and strong ignition. But I think that that's another area that this scaling argument can be extended to come up with more generalized criteria. So, so I'm standing between you and lunch, maybe the discussion too. So that's about it. I hope you enjoyed the sunset last night. And thank you very much.